So thanks for joining. Today we have another talk on P4, and I promise that we did not do this on purpose. It was just luck of the draw for our speakers this year. But we have two great speakers, good friends from the University of South Carolina, Jorge and Elie, and they are going to be talking a little bit about their work on P4 programmable data plane switches and working with offloading media traffic. And we're going to have two different speakers here, so there'll be a handoff at one point, but Jorge is going to get us going. So take it away, Jorge.
Thank you, Jason. Good afternoon. I'm Jorge Crichigno from the University of South Carolina. I will be presenting the first part of this work, then I will turn to Elie. I'm in the IT department here at USC. Elie is a PhD student working with me. We did this work with Elias Buhar from Texas, and we're fortunate to have the input also from Vladimir Gurevich from Barefoot Network. He helped us improve this work. This is going to be presented in ICC 2020. So I will start with the introduction and then a little bit of background about SIP and RTP protocols. Those two protocols are used for media. That means voice, video over IP. Then the type of problems that exist when dealing with NAT and media. And then I will talk a little bit about P4 switches. And then Elie will be presenting the solution to these problems, some evaluation results, and some lessons that we learned. First, according to some estimations, media traffic represents approximately 80% of the total traffic over the internet. So much of this is generated by end users communicating with each other. Media services, we will be dealing with, in our test, we deal with a voice, but this includes voice and video, typically run alongside the data network in campuses. That's our case at USC. There are some open protocols, and then we have the proprietary protocols. Two examples are Skype and WhatsApp. Now, when talking about open protocols, open standards, we have to divide these in two categories. One is the protocol or protocols that are being used for signaling, to establish the session, to manage and to end the session. And the most popular protocol is SIP. And the protocols that carry the actual data, the voice and the video. And an example is RTP, real-time protocol. We use these two protocols in this work. So we will be back to SIP and RTP in more detail later. Now, just to keep in mind, when dealing with the voice, video, media in general, there are some desirable QoS characteristics. For example, we would like low delay, low jitter, and media sessions tolerate occasional losses, but we would like to minimize losses as well. A little bit more of detail about signaling and the relation between SIP, RTP, and this is key to understand the problem. First, SIP is the protocol that initiates, maintains, and terminates media sessions. So in this example here, we have the two end users. UIC is the client. the server is the other party, but both end devices can generate, or both in general generate the traffic. So SIP is important to establish this communication. And this is the typical case. There is a SIP server. There could be more than one, but the end users register to this server. That's why we call also the register. Once the sessions are established, the actual communication go directly from A to B. That's the RTP traffic. Now that's the ideal scenario. In reality, there are many devices in the middle, including NAT. And then that's where some problems occur. In particular, NAT introduced some issues, the traversal of end-to-end sessions. This is a reference, an interesting paper that I read recently. This is from Qaeda and how spread the use of NAT is. That's just for reference. But back to the problem, what exactly is the NAT problem when dealing with media? Well, the first potential problem is that NAT prevents a user from the outside network from initiating a session. And that is solved by using NAT, a SIP registrar service. So basically, if I want to receive calls or establish a session, I have to register somewhere to the SIP register. Analogous to registering to Skype register server, supernodes, what is known in Skype. But the second problem is that the signaling protocol, in our case, we made tests with SIP. The signaling protocol carries the IP address and the port number that will be used by RTP to send the actual traffic, to send the media traffic. And in particular, especially, the port to be used is unknown at the time of establishing the session. So that's why we highlighted here. Ports are unknown until RTP traffic starts. Why? Because the NAT device will translate those ports or may translate those ports. Now, this is a well-known problem, and there has been some solutions for this. We listed 3 solutions: RFC 5389, 7566, and 8445. And it's down here. So those these solutions, this RFC, if you go and read those RFC, they refer, or the way to solve this is by using relays. And in fact, for example, TURN stand for traversal using relay around NAT. So at the end, there is a need of a relay server in the middle of the 2 devices once we were using NAT. So what is the idea of having a relay server? This is the scenario. The relay server is just an intermediary device. And then we have the end users A and B and a SIP server. This is the topology that we use for testing purposes. We could have more than one server, SIP server. A and B can be registering to different SIP servers, but this is the basic idea. The SIP server will be in communication to the relay server, and the relay server will be used as a man-in-the-middle type of device between A and B for RTP purposes. That's why we have on the right-hand side this table that is recording or will record information about A and B. Now, at the beginning of the communication, we have SIP establishing the session. So we have a user A with an IP address A. These could be private IP address, and a port A. This is referring to transport layer port. And these are the IP addresses and the IP address and the port that will be used by RTP when the communication starts. But again, the problem here is that RTP didn't start yet, and therefore the NAT device didn't map yet the port for the device A. So this information is recorded in the relay server. We have the relay server is recording IPA prime. IPA prime referred to the translated IP address for the device A. And notice that the port is not recorded at this moment. And again, why? Because the RTP traffic didn't start yet. The way around this is having the relay server allocating a port for the device A on behalf of device A. So that's what we're referring here to PRA, and it's the green port here. So the solution around is the relay server allocate these two ports, the same for or another port for the device B. And this information is communicated to the end devices through SIP. So at a given point when the communication starts, user A will forward packets or will forward RTP traffic to IPR, which is the IP address of the relay server, port RB, which is the port allocated by the relay server for the device B. So once the session is established, RTP traffic starts flowing, and it's only at that point when the relay server learns what are the actual ports that are being used by A and B for RTP purposes. With that information, the traffic can be relayed to the end users and the communication starts. So that's the idea of the relay server. Some highlights from this slide are, at this point, the relay server is really just forwarding traffic based on this table that we have here. So we are recording the IP addresses, the ports, and at the same time, the relay server is modifying the packets before forwarding to the end devices. So it's a simple operation, and we will use this fact later to do it in the switch. Now, why did we believe this was a good use case for programmable switches? Well, the programmable switches, the P4 switches, permit us to program the data plane and add proprietary features. In our case, or to solve this problem, there were a few features to add. First, we had to parse the packets, including the UDP header. This is something that a regular switch wouldn't do it, but we can specify in our program to parse the UDP packet. Then we would like to inspect the header. We want to identify the session a packet belongs to using the 5-tuple. That means source IP, destination IP, source port, destination port, and transport layer. Transport layer would be UDP because RTP is encapsulated within UDP. And finally, P4 switches also allow us to modify fields. We have to modify the IP addresses and ports before forwarding to the other side. So we exploit this fact and we come up with the conclusion that this can be implemented in a PISA device. PISA is a short for protocol independent switch architecture. This is the model used for programmable switches. Essentially, we program a parser. In our case, we will parse all the way to UDP headers. Then Once it's done, we will do a hash operation so that we can identify the session the packet belongs to. That is, and then we will try to match that with a table that we have. And then the action will be modify or change header fields. And finally, in the programmable, the parser will encapsulate again the packet to be forwarded to the other end. Now, this is our proposed solution. I will turn to Elie that will continue from here.
Okay, so hello everyone. I would like to continue from here to explain the proposed system. So basically, the proposed system will use the programmable switches to emulate the behavior of a relay server. So basically, the P4 switch will parse an incoming packet that carries media traffic from the first party. In this example here, we have user A. And then it will identify the session to which this packet belongs by hashing the 5 tuples that Dr. Jorge just mentioned. And after that, it will modify the packet headers by replacing the source IP with the relay server's IP, and the source port with the port allocated by the relay server to receive traffic from A. At the same time, it will also modify the destination IP and destination port with those of user B. And since we modified the packet in the switch, we have to recalculate the checksums. And after we recalculate the checksums, the switch will forward the packet to the other user, user B. So we developed a software which we refer to here as the agent that will learn the ports allocated between the SIP server and the relay server. And this agent has a component called rule generator that will use these 5 tuples allocated to the media session in order to construct that identifier. And after that, the rules manager component will push the rule to the programmable switch. At the same time, it will push the header values to be modified in the packet. So the agent also is responsible for checking when there's a call to be teared down so that it releases the resources from the programmable switch. Basically, we do this by learning if there's a SIP-by message received on the server, and accordingly we determine the session, and then we can release that allocation from the programmable switch. So for the implementation, we use the following components. So we use OpenSIPs, which is an open source implementation of the SIP server, RTP proxy, a production grade relay server, which is used to relay RTP streams. We use also SIP-P, an open source tool that allow us to create concurrent calls at the same time generate RTP traffic. We also use iPerf to generate some background UDP traffic while we initiate the calls. And finally, we use the Edge Core Wedge 100 BF as the programmable switch. And this switch has the Tofino programmable chip from Barefoot Networks. And we have here 4 servers, as you can see in the topology, connected through the switch using 40 gig links. And each server has 4 cores running. So for the evaluation, we considered 2 approaches. The first one, which we refer to as the server-based relay. This is where we use the relay server to relay the traffic. And the other one, which we call the switch-based relay, this is where we use the switch to relay the traffic. We considered generating 900 media sessions and at the rate of 30 sessions per second. And we executed the test for 300 seconds while using the G711 media codec, which has 160 bytes payload with 20 millisecond packetization rate. We evaluated several metrics. So first, we evaluated the delay, which is the time interval starting when a packet is received by the switch ingress port and ending when the packet is forwarded by the egress port of the switch. And by evaluating this delay, we are able to define the delay contribution of both the switch and the relay server. So this graph shows the CDF of the delay in both approaches. And in the server-based relay, we had the mean delay of 6.88 milliseconds with standard deviation of 3.74. Whereas in the switch-based relay, we only had 440 nanoseconds with very, very small variation in the delay. We also evaluated another metric, which is the delay variation. And this is calculated by taking the absolute value of the difference between the delay of two consecutive packets. This is similar to what's known as jitter, and this is defined in RFC 4689. This graph also shows the CDF of delay variation here. You can see that in the server-based relay, we had the mean of 0.26 milliseconds and standard deviation of 0.57 milliseconds, whereas in the switch-based relay, we had negligible delay variations. The mean and the standard deviation are listed here in the graph. We also evaluated the packet loss rate by considering the sequence number inside the RTP header. So in the switch-based relay, there were no packet loss. In the server-based relay, there were few packet losses, but we also when we executed the test using different number of concurrent calls, we noticed that the more sessions we have, the more loss rate we will witness. We also evaluated the CPU usage on the relay server. And in the server-based relay, the CPU percentage climbed to 80% when new sessions were entered. And then after the sessions were allocated, it dropped down to approximately 50%. In the switch-based relay, when new sessions were coming, it peaked at 15%, and then it decreased back to approximately 0% with some spikes here contributed by the operating system. We also evaluated another metric, which is called MOS, the mean opinion score. This is an estimation of the quality of the media session. It was standardized by the ITUT, and the maximum mean opinion score that can be attained using the G711 codec is 4.4. So these three graphs show the CDF of the mean opinion score for 750 calls, 1500, and 1800 calls. You can see that in the switch-based relay, in all three scenarios, we achieved the maximum mean opinion score, which is 4.4, whereas as we increase the number of calls using the relay server, the mean opinion score starts to decrease. And the more this value decreases, the quality, of course, will degrade. We also evaluated the resource consumption by the switch. So to do that, we considered two different approaches. The first one is where we implement the relay functionality that we proposed on top of a baseline switching program known as switch.p4. This program has different functionalities such as layer 2, layer 3, access control list, quality of service, and other. And the other approach is where we implemented the solution as a standalone program. And this table here shows the additional hardware resources used with both approaches. So on top of switch.p4, with a table size of 64,000, the SRAM increased by 16.2%. And the table size here reflects the number of sessions that will be allocated. In the standalone program, however, we were able to accommodate 1,050,000 entries with some additional resources to spare. And we also evaluated some other resources such as hash bits and tcam, and these are also depicted here in the table. So what are the lessons that we learned? First of all, we saw that there's a huge improvement in the performance. So 1 million sessions in the switch can be compared to 1,000 sessions per core. The quality of service parameters such as the delay, the variation of delay, packet loss, and mean opinion score were also improved. We saw that because we are programming these switches, we have more flexibility to create new applications, modify these headers to use some non-standard fields. At the same time, when we did the experiment and we evaluated the timing information, we noticed that taking timestamps on the switch will result in high resolution timing information. Also, the programmer can free the unused resources and can avoid complex application logic in order to accommodate more media sessions and to overcome the limitation of the resources of the switch.
Thank you, Elie. Elie, could you go to the previous slide, 24?
Mm-hmm.
Something that I want to point out here, I would say, I think this topic was brought the last week. The limited resources, what we notice is that whenever you do an upload or offload some functionality to the switch, you have to be careful with the limited resources. In our example is if you want to accommodate more media sessions, we had to remove some features that we were not using in the switch. For example, QoS related features or ACL. That's what Elie did in order to accommodate more sessions. The other is avoiding complex application logic as much as possible, because if this start being complex, it's hard to compile, and if it doesn't compile, you cannot implement in the switch. So really, this was a good application in the sense that the relay server is just relaying packets, making some modifications and then relaying. So that's why we believe that that was a good application. Lastly, in the last slide, just want to make sure that we recognize NSF, because our lab here at University of South Carolina is funded by the National Science Foundation. At this point, Jason, that is the presentation. I don't know if there is any question.
Sure. So thank you guys for doing this. Really interesting stuff, and a good follow-on to what we saw last week. So we do have one question from Malathi. Can you show slide number 14 again? Couldn't we set up a 4-tuple-based packet forwarding entry in an off-the-shelf switch? Do we really need P4?
Elie, do you want to, or do you want me to answer that, or do you want to?
Sure. Go ahead, sure.
So the question, if I understand, can we use a 4-tuple base? I have to think about that, but a regular switch won't be able to. I have to think if. But I don't think that you will be able to modify the header fields, source IP, destination IP, source port, destination port, and also I am not sure how with a regular switch you will modify these tables dynamically. In particular, this one table that is used to forward the frames. That's the. I don't want to say no. I have to study, but at least from the top of my head, I don't think that would be viable with a regular switch. Elie, I don't know if you have any input on this.
Yeah, I agree. Yeah, I think that due to the programmability of P4, we were able to do this, to parse, to go up to the UDP and to take all these fields to calculate that, that hash, identify the flow, and accordingly do the relay automatically in the switch. So we are updating the values and at the same time recalculating the checksums. Yeah, this might not be possible in normal switches.
Okay. And Malathi had a follow-up on that one, maybe at the scale of handling many sessions. And then June also had a similar question. Is the task possible with an open flow switch too, with the controller installing, removing table entries?
It might. I don't have. I'm not an expert in SDN. I will defer to Elie. Elie, do you have input on this?
Yeah, we have to think about this more, but I think again the same like idea that we discussed, where we need to modify these headers directly on the data plane and still achieve the line rate. I'm not sure that we can do that in an open flow switch.
Okay. So Michael had a question. If your SIP sessions were all native IPv6, so you could avoid NAT issues, would it still be advantageous to use the P4 switch relay approach?
I think it could still be. I agree with that observation in the sense that you don't need to forward to the relay server. Oh, sorry. If I understand well, where would you put the programmable switch? I'm looking at the figure here in 14. If I can ask this person, that might solve the problem using IPv6.
Yeah, Michael, if you can type in, or if you're in a quiet area, you'd want to unmute yourself.
So the relay server, the idea of relay is, yeah, to this particular IPv4 problem where we use NAT.
I would also add one more thing. I mean, if we are using IPv6, probably removes most of the issue that we face in current NAT, but still in most deployment, organization will still need to have a relay in order to perform some lawful interception, maybe, or some other type of monitoring, maybe voicemails or something like that. So basically, in such case, if the relay will be there, so the program switch will still provide value, even if you are trying to use IPv6.
Okay, thank you. So we don't have any other questions right now, but if people have more, please type them in. I had jotted just a couple down. So have you guys tried to deploy this on your campus network, or are you just doing this as simulations for right now?
We're doing it in our lab. So we didn't deploy in the campus yet, even though we use voice over IP here at USC.
Yeah, I'd be curious to know if in a real world setting, if these would hold true, because some of those performance gains look really, really good. Any sort of thoughts on if you were to take this from the simulation into the concrete world, what challenges or sort of risks there would be to trying to implement this?
Yeah, yeah, I agree with you, Jason. First, there will be latency. What we measure here is only the latency of the subsystem including the switch plus the server. So in the real world scenario, there will be more latencies that play. For example, if this is going through a wide area network, sure, we didn't consider that. And there will be more jitter and more packet losses. But anywhere where you can minimize the delay, that's a good thing. Real world scenarios, I used to work before coming to the academia. I used to work in a ISP that provided this service. And we had a very similar scenario, a zip server with relay server. And it was exactly this scenario that we have here. So I'm thinking that this would be a good setting for the ISP that was offering this service, because you still minimize the overall delay. And in our case was substantial in the relay server. I don't remember Elie, how much did you get, but it was in the milliseconds. So any reduction is good.
Okay. And then you may have said it, but if you did, I didn't see it fly by. What brand of programmable switch is this right now? You said it was a barefoot network switch?
Yes.
Yeah. Go ahead, Elie.
Yeah, it's the H-Core Wedge 100BF32. It's a programmable switch provided by Barefoot Networks. It had the Tofino chip, and it's 3.2 terabit per second overall switching capacity.
Yeah, I think the last week presentation, I'm trying to remember if it was H-Core also, but the brand is H-Core. The chip inside the switch is Barefoot Tofino 1, as Elie said, 3.2 terabits per second.
Okay. Well, I don't see any other questions, so we'll pause another minute or two in case anybody has any last things they want to ask. I want to thank you both again for doing this. I think it looks really neat. Since we have a little bit of extra time, Jorge, do you want to say anything about sort of your training activities or your upcoming workshops if people want to learn more about this?
Sure. I will share the screen then.
Okay.
Share. Jason, I was not. Give me 1 second. I don't know. Is my screen being shared at the moment? Yep,
you're good.
Okay, so actually we have one training workshop in Tampa. It's organized by University of South Carolina, also by the Engagement and Performance Operations Center, Jason. So this will be a training in high-speed network protocols and security. So we have an NSF grant where we develop this training material, and this workshop is in particular for BGP and for intrusion detection systems that are useful for science DMCs. That means offline intrusion detection system. We will be using SIG. And also network tools and protocols. Basically, if you are familiar with the ESNet website, you might find information such as emulation of wide area networks using NetDem. So all these will be touching will be covering the workshop. That will be May 4th and May 5th at the University of South Florida. And there is a tentative agenda, but if you are curious what the type of activities that we will be doing, here are some labs. There are 14 labs in network tools and protocols. Border gateway protocols, we will be using FRR. And by the way, at the University of South Carolina, we use FRR in our programmable switches. So FRR is a router implementation that includes BGP. So there are some labs. For more information, feel free to click the PDF. And actually, if you want to test this, I can give you access to our virtual environment. So all this is already implemented. And then we have some virtual lab for Bro and SIG So that's what we're going to be doing in these two workshops, in this workshop in Tampa. I said two workshops because there will be a follow-up workshop at the University of South Carolina in July. Jason, I don't know if you want me to add anything else or if I cover everything. You are the core organizer of this workshop.
Nope, I think that's good. And just as a note to everybody, we'll certainly announce this workshop when the details are finalized. If people are interested in attending or want to suggest anybody that attends, these are really targeted at sort of people who may not have all these skills, or those that want to freshen them up, but also those that could really benefit from learning some of these new technologies. So certainly, if anybody's interested, shoot us a line, and we'll make sure that we give you the info. All right, well, I don't see any other questions, so I think we'll end for today. Thanks everybody for joining. We will have another talk next week. It's going to be on related to Globus and the Globus Toolkit's authentication protocols. So I will send out information about that shortly. Hope everybody has a good weekend, and we'll talk to y'all soon.